Hey, welcome back to Mr. Naylor's workshop. We're going to build on yesterday's lesson, but as we continue talking about matrices. Now, today we're going to learn about what's known as a determinant and an inverse. It's going to be a little more mathematical, but I'm confident that you'll do well with it, and hopefully it will bring some more sunshine to your day. So let's get started with determinants. Now, you'll find out that a determinant is actually a single number. And for a 2 by 2 matrix that would contain entries of A, B, C, and D, we can find the determinant of that matrix, that is a single number, by following just this simple formula. It's AD, which you'll notice, I hope, is the product of the diagonals, minus BC, which is the product of the other diagonal. There's a little bit of notation here. First of all, when you see the abbreviation DET, that stands for determinant. And also when you see these absolute value type bars, basically missing the little brackets on each end, when you see just that absolute values style around a 2 by 2 matrix, that's also tells you to do the determinant. All right, now, you want to see if we can do the determinant for a couple matrices? Sure. Here's a 2 by 2 matrix. It's got 7, 9, 3, and -8. Now you'll notice that we have just like those straight bars around it. That implies determinant. And of course, to find the determinant, all we got to do is multiply the numbers in the primary diagonal. So when we multiply those numbers, obviously we're going to get -56. And then there's always a subtraction sign that's part of the formula. And we'll multiply the numbers in the secondary diagonal, and obviously that comes out to be 27. So we have a little -56, a -27, and that equals -83. So we would say the determinant of that 2 by 2 matrix is -83. Here, let's try another one. What if we throw in the variable x? And we see that it's part of this 2 by 2 matrix. And we even are told that this is going to equal 28. You think you can make up a little equation and solve for x? Go ahead. Good time to pause the video and see if you can set this up on your own. How'd you do? Did you follow the same rule? Did you multiply the primary diagonal? That would come out to be 4x. And did you put a subtraction sign in? There's always a subtraction sign in the determinant. Multiply the secondary diagonal, we get -3x. And that's supposed to equal 28. All right, so of course 7x equals 28. And we just solve for x. Not too bad. Kind of easy little formula for 2 by 2. What about a 3 by 3? You might see here that it says that if your matrix is bigger, that you have to use something known as an expansion by minors. Well, an expansion by minors isn't a formula. It's more of a process. And it kind of says, it does what it says. It takes this 3 by 3 matrix and it expands it out into minor matrices. And I'll show you when we expand it out into minor matrices, we can actually find the determinant. Now, if we were in class, you would see me with my hands doing a few more things. We'll try to show you here in the video. But basically, we're going to, well, you could expand across any row or column. I'm going to choose to expand across the first row. Now, when I expand across the first row, I will basically encounter each column one at a time. And when I encounter the first column, I see that the intersection of those two columns, they share the number 8. Excuse me, if that row and column shares the number 8. So the number 8 is going to end up being a coefficient. And you see the minor matrix. I wonder if you do. Do you see the minor matrix? It's the 5, 7, 2, 4. That minor matrix is going to get written beside the number 8. I need to get rid of some of these extra lines so that we can keep working through the problem. But again, we have the number 8, and we have this minor matrix of 5, 7, 2, and 4. And you'll see, I hope, that I wrote them as a 2 by 2 matrix. And just a little hint, in a moment we will be able to find the determinant of that little 2 by 2. But we're not done yet, because we're still expanding across the first row, and we ain't got to the next column. When we get to the next column, we find that they cross over at the number 9, and they leave behind a minor matrix. That's right, the minor matrix would be this set of 4 numbers. Let me get rid of some of this, and we will take the number 9. We'll put that down as a coefficient, and then the minor matrix of 3, 7, -1, and 4. Do you think you know what the last coefficient is going to be in the last minor matrix? We're still using the first row, but we get to the last column. We see the number 3. That's the shared number. And then we see this minor matrix. All of that gets written down. So what do we got here? We got a 3, and then a minor matrix of 3, 5, -1, and 2. Now, right now, it kind of looks like I got like 3 separate problems just sort of floating around. It turns out that these 3 problems, these 3 matrices get connected. They get connected with some plus and minus signs. Sounds like somebody's letting the water out of the sink upstairs. So the first one is going to be a plus sign. The next one's going to be a minus sign. And the last one, can you guess? That's right, it's going to be a plus sign. Now, because we went across the first row, we always will follow the pattern plus, minus, plus. More on that in a moment. For now, we actually can calculate some of these determinants. In fact, all of them, right? Here you should feel like you're seeing 20 minus 14. 20 minus 14, certainly that determinant can be calculated to be 6. What else do we have here? -7 and 12. Now be careful, it's -7 minus 12. Okay, so that's going to come out to, of course, be -19. And then you want to calculate the last one. 3 is still the coefficient. Get a little 6 minus -5. 6 minus -5. Again, we get a determinant of 11. Now, when you combine all these numbers together, obviously you do the multiplication, subtraction, and addition, put them all together, we're going to get our final answer. We're going to end up with the determinant. That's the determinant of the original matrix. Now, it does come out to be -90, but to kind of emphasize that, I want to put that beside my original 3 by 3 matrix. It's called an expansion by minors. We went across the first row. If you're already wondering, could you have gone across to any row? Yes. Or any column? Yes. You can actually expand any row or column. I'll give you a problem to try in a second. Before we do that, I want to add one more thing, and that is that there's always a pattern. In fact, whenever you have a 3 by 3 matrix, you can always be assured that no matter which row or column you expand, that the first number, second, and third number will be a plus, minus, plus. The next one would be a minus, plus, minus. And then, can you guess what the last row would be? That's right, it goes back to plus, minus, plus. So if I expanded with any row or any column, I would choose these plus and minus signs in front of each of the coefficients. Try one. If we were in class, I would give you time to try it. So go ahead, try this. Again, good time to pause the video and see if you can find the determinant of this 3 by 3 matrix. Now, as you copy down some of the numbers, notice that there are those, so to speak, absolute value bars. It's not actually absolute value, but there's those straight bars, which implies to do the determinant. And you can actually expand to any row or column that you want. I'll just let you know that I'm going to do the first row again, but those of you that are a little more daring, maybe you'll expand another row or column and see if you can get the same answer. All right, if you expanded, or as we expand with the first row, we end up with a coefficient of 4 and a minor matrix of -1, 5, 6, and 1. I'm going to go ahead and put a plus sign there right now. And in a similar manner, I'm going to go ahead and put this minus sign here. Minor matrix of 2, 5, negative 3, and 1. And then the last coefficient is 0. Ooh, wait a minute. A coefficient of 0? Doesn't matter what I put in that 2 by 2 matrix. All right, you'll find out that zeros can be very helpful when it comes to finding a determinant. Okay, so how's some of the in-between numbers here? We should end up with a determinant of negative 31. Here we should end up with a determinant of 17, right? And of course, the last one, we know that it's going to be 0 no matter what. So how'd you do? You should have gotten negative 2, 2, 6. Negative 2, 2, 6 for that determinant. Now, maybe you're wondering, what is the purpose of the determinant? Make sure you stick around because I'm going to show you. But for now, it's a single value. And it's a value that will be used to calculate some interesting things. Next class period, when we're together, you'll find out that we can actually find the area of a triangle using a determinant. And then in today's lesson, in a moment, we'll find the inverse of a matrix using a determinant. Well, before we do any of that, I want to offer to you a bucket O bonus. Yes, there's a bucket of bonus that comes with today's homework. It's number 28, and it's going to be a 4 by 4 determinant. It's going to be a 4 by 4 determinant. Now, maybe you're just wondering, what's a bucket of bonus? Well, there's a bucket of bonus points, and I found a dirty old bucket in my workshop here, and inside that bucket, there is an undisclosed amount of bonus points that will be dumped on whichever student gets the problem right. If a lot of students get the problem right, then the bucket of bonus will be distributed equally to each of those students. There is a guaranteed minimum payout. So if you get number 28 correct, you will be guaranteed some bonus points. But again, we will look inside the bucket to see how many points get distributed depending on how many students get the problem right. So, number 28. Well, I want to reveal or at least discuss a few thoughts, mainly your approach. And since, of course, it's going to be a 4 by 4 matrix, your first very important order of business is to understand that this plus minus plus pattern continues into larger rows and columns. And as you start to expand, maybe the first row, and you cover up that first row and column, what do you see? Yes, you see a 3 by 3 matrix. What will you do with that 3 by 3 matrix? Right, you'll have to find the determinant of it. How will you find the determinant of it? By doing another expansion, that's correct. So the problem becomes a challenge as to how well you can organize each of these rows and columns, the coefficients that go with them, and the resulting minor matrices. All right, that's why we call it a bucket O bonus. Now, you have to show the work. If by chance you get the determinant with some other method, that's nice to check your answer, but you have to show the work. And that is ultimately what's going to earn you those bonus points. All right, I'd say if there's any questions, but it's hard for you to ask me right now, so you could drop me a line if you really want to. Otherwise, enjoy number 28. Are you ready to keep going? Let's carry on with some special matrices. Now, these two matrices that are in yellow, they're being multiplied together. Matrix multiplication. Yeah, what we talked about yesterday. So let's go ahead. Let's multiply them together. Remember, row times column. And a little bit of simple math here. You should see 4 and negative 3. But when you add those together, you end up with, that's right, you end up with the number 1. Okay. How about the next column, of course, times the same row? What do you see? Do you see 6 and negative 6? Yeah, when you multiply 6 and negative 6, you end up with 0. Okay, something special is happening here in this green matrix. Next, are you thinking about it? That's right, you end up with 0 again. And when we multiply the last row and the last column, we should see negative 3 plus 4. Negative 3 plus 4 is 1. So what's going on here? What have we created? Well, we've actually created a special matrix. This matrix over here, this is interesting. We seem to have some things that are kind of scribbled out. I feel like this is like a lottery ticket. I get to erase and see what I won. So let's see what we won here for this green matrix. Ready? Scratch it off. And, oh, cool, I get the identity matrix. Now, the identity matrix is a matrix that contains ones in its main diagonal and zeros everywhere else. And we call that the identity matrix. More on that in a moment. But you see, what's really important here, what's really kind of special here, is the two matrices I started with. And these two matrices, when I multiplied them together, produced the identity. So that means that they are, you ready to scratch it off? That means that they are inverse matrices. Now, inverse matrices, when multiplied together, will give you the identity. In fact, anytime in mathematics when you have inverses, mathematical inverses will always create the identity. What do I mean by that? Well, just take a little walk down sort of mathematical road with me for a second. Back in like first grade, when you took 1 plus negative 1, you actually were adding inverses. Now, when you add inverses, you end up with the identity of addition. What does that mean, the identity of addition? Well, what happens if you add the number 0 to something? That's right, you get the same value. You get the identity of that. So that's why we call 0 the identity number of addition. Now, maybe when you got to third grade, you were asked to multiply. You were asked to multiply some inverses. What happens when you multiply inverses? That's right, you get the identity number of multiplication. Okay, of course, the number 1, when multiplied, will produce the same value. And a little bit later, maybe like in high school algebra, you took two functions that were inverses of each other. Function composition of two functions that were inverses. And well, when you do that, you end up getting the identity function. Now, the identity function is such that if I input into it, I will end up with the same output. So I'll end up with the identity. So that's just kind of a fancy way for the teacher to say, hey, we've got some special matrices here, because these two matrices, matrix A and its inverse, when they were multiplied together, created the identity matrix. And sometimes we put a little bracket around it just to kind of make that stand out. And the identity matrix is a matrix that you'll find out always produces the same result when it gets multiplied to another matrix. Well, inverses is our next simple conversation, and it turns out to be a formula. Now, if I want to do the inverse of a 2 by 2 matrix, I end up needing sort of two parts. I end up needing this, you'll learn, to be this sort of this fraction out front. We call it 1 over AD minus BC. AD minus BC, I feel like I've seen that before. And then the numbers in the matrix go through a little switcheroo. In fact, the numbers in the main diagonal, the primary diagonal, their location switches. And then the numbers that are in this remaining spot, the secondary diagonal, they become the opposite. And so when I put all this together, I end up with the inverse. I had a student once kind of like turn this into more of a diagram with some notation, and I liked it. So I stole it with permission, of course. And so it's really 1 over the determinant. Again, that often will end up being a fraction or maybe some coefficient, but 1 over the determinant out front. And then we can see we switch the diagonal and we make the other numbers the opposites. And that will give us the inverse. Let's try it. It's a little formula. Here's a matrix, 4, 6, 1, 2. And I want to find the inverse. Ready? To find the inverse, I have to follow this step, or follow these two steps. I'm going to have to first get the determinant. Often that's something that kids kind of do off to the side or wherever you want to do it. So we've got the determinant. I think that's just going to be like 8 minus 6. Remember, that's multiplying the diagonals. And of course, that comes out to be 2. So what that means is that I'll be able to put 1 over 2, that's of course the number 1/2, in front of my little switcheroo matrix. Now my switcheroo matrix is just going to make me change the position of those, the numbers in the primary diagonal. So now I have a 2, then a 4, and then we'll make the other numbers the opposite. So I have a -6 and a -1. Now, please understand that this number out front, this is a scalar number, and just like we learned the other day, a scalar number is and should be distributed into a matrix. And so when I distribute that in, I end up basically dividing every number by 2, and of course I get a more simplified result, and just maybe I get something that looks kind of familiar. Do you feel like you've seen that matrix before? Yeah, that's right. It was already shown to be the inverse of our original pair of matrices. So we kind of proved it 2 ways. You multiply them together and you get the identity, or you actually follow the formula and you get the actual inverse. All right, and we can call this matrix, we can call it A inverse, just to make it a little more official. Why don't you see if you can find the inverse of this matrix? We've got a 3, a 2, a 5, and a 3. Yeah, go ahead. You should be using the inverse formula. Okay, did you find the determinant? It's just going to be a little 9 minus 10. So the determinant comes out to be -1. Following the rule, I'm going to put 1 over the determinant. So that, of course, is just 1 over -1, which is -1. And we'll go ahead and kind of switch the numbers. Except when I switch the main diagonal, it still looks like the same. But anyway, I'll put an opposite on the other numbers. And yeah, just take a negative and distribute that to the inside. So we're going to basically just multiply everything by -1. And we end up with a final answer of -3, +2, +5, and -3. Okay, now sometimes students say, "Are you sure?" And I say, "I don't know. How would you check it?" There's a way to check it. Not look in the back of the book, silly. You could multiply it. Yeah, you could multiply it by the original matrix. And so if I wanted to, and since I want to, I'm going to multiply these. Okay, now you got to actually do the math. Looks like I get -9 and 10. That's good so far. That comes out to be 1. When I multiply it to the next, I see hopefully -6 and I miscopied this. So now I get -6 and +6. So that comes out to be 0. And if you run through the last row, you find out that once again you get the identity. Okay, remember the identity is a matrix that has 1s in the main diagonal and then 0s everywhere else. Well, what if I asked, as a final problem, what if we wanted to find the inverse of this? It's not going to take too long. As you'll see, when I start to do the inverse, first thing I need is the determinant. And when I do the determinant, I end up with a little 12 minus 12, which last time I checked is equal to 0. Well, that's right. If you're going to do the inverse, you're going to be forced to put that 0 in the denominator. And I'll tell you what, you can stop right there, because we know that when you have a 0 in the denominator, that you have an undefined value. So the inverse does not exist. The inverse is undefined. And that'll be something special in a few days when we actually use these matrix operations for a practical purpose. Determinants and inverses. So you ready to do a little bit of homework? Of course, don't forget about the bucket of bonus, but on page 533 and page 525, I encourage you to do it in the order that I presented it here. You'll see some determinants and you'll see some inverses. And I hope that I'll see you tomorrow.
Some of you asked if I would give you a quick tour of my workshop, so certainly come on in. I'll show you around real quick here. Now, this is a low-tech operation, so bear with me. But behind me, you'll see my lumber rack. You always need some lumber to make your projects. I probably need to clean that up a little bit. You end up with a lot of scrap wood. Next, we have the planer. You always need a planer that takes your wood that's rough and gets it down to more of a finished surface that we can work with. Now, this tool right here is called a joiner. Your joiner is really what is used to get a straight edge on one edge of your wood. You just run that through there upright. My wife will tell you a story of once when I had to come running upstairs with half my thumb sliced off, and boy, did that hurt for a while. But be careful where your fingers are when you're using a joiner. Now, the workhorse of the workshop is you need a table saw to do just about any project, and it truly will make about any cut. This one's solid. It's a cabinet grade saw, but I certainly enjoy the table saw. Now, as we work around the shop, we've got some other sort of specialty items. Over here is my bench top drill press, and it also doubles as a sander if I want to put some sanding drum in there. We've got the cutoff saw that makes some quick work of getting square edges, and dirty old sink that my wife thinks that I need to clean up a little more. We also have a router table. I built this, but the router table is what is able to put sort of fancy profiles on the edge of wood. I don't have anything in there right now. And what else do we have? Yeah, hey, here's my workbench. Do you recognize the top of that? That's right, it's from the Red Line Bowling Alley. Actually, when they redid their lanes, I went down and got a piece of that. And well, it's certainly served its purpose. We also have a bandsaw back over here, and some sanding equipment. These are used depending on the types of curves, cuts, and so forth. And some of you noticed that we were working on some welcome signs. That was actually my wife's idea. That was more of a crafty project. And then this white bench here, I was able to just work on this week. My wife wants to put some plants on there. I haven't had too much time in the workshop. It's been a busy school year, but it's been nice to get down and do some woodworking instead of always math lessons down here. All right. Hey, you be good. You enjoy your day, and we'll see you tomorrow.